Okay, so what we were looking at in the last classes, we looked at a concept called capillary model, okay, or tube model, right? Okay, which is a methodology which has been developed to basically correlate delta P by L, which is the pressure drop per unit length of the packed bed, okay, to properties of the packed bed, okay, in terms of uh, V naught bar, which is the superficial velocity, right, of the liquid that's flowing through the packed bed, mu, which is the viscosity, 1 minus epsilon whole square divided by phi s square into dp square times epsilon cube, right? That's what we had developed. Was that? Yeah. So what we said is that when we the way this was done is we so we are basically looking at a case where you're looking at laminar flow conditions, right? Okay, right, laminar flow conditions, and the starting equation was delta P by L is equal to 32 mu V bar divided by um, d square, right? And then what we did is we used this capillary model, and then we did the surface area balance and the volume balance, and we said you would have to replace your d by d equivalent, okay, which was something like 2 by 3 into phi s into dp into epsilon divided by 1 minus epsilon, right? Yeah, okay. And then this v bar, which is the average velocity with which the liquid is flowing through the conduit, right, that we would have to replace by v naught bar divided by epsilon, right? That's the modification that we did. And if when we worked it out, this the constant here, it came out to be something like 72 times lambda, right, lambda 1, okay. And we said that people have done a lot of empirical lot of experiments, and they found out that this if you do an experiment of delta P by L versus if you have a data of delta P by L versus V naught bar, right, and if you're in the laminar flow condition, that is if you ensure that your Reynolds numbers are less than 1, you would get a straight line that is passing through the origin, and if you know the other factors, right, this is basically your slope is going to be this time some constant, right, and people have found that that is of the order of 150, okay, which basically gives you your lambda 1 as 2.1. So I was trying to discuss that yesterday, said that this 2.1 accounts for the fact that the liquid is not flowing through straight pipe, but the pipes are tortuous, okay. In essence, how high this number is, if it's much larger than 2.1, then it will be much more tortuous, okay. If it is closer to 1, you can say that it's like not too tortuous, okay. That's the you can think of. Now what you can do is I can actually recast this equation into something like this: delta P by L, okay, is equal to I have this V naught bar and mu at the top, and at the bottom you can write it as K, and K essentially, from if you look this up, K would be something like phi s square into dp square into epsilon cube divided by 150 into 1 minus epsilon whole square, right. So I'm basically, I've taken this expression. Oh, I just forgot to mention that this equation is what is called as a Kozeny-Kármán equation. Okay, that's because these people developed this equation. See, these are the developments that happened in 1930s and 40s. The fact that these models are still used in predicting pressure drop through packed bed is a testimony to the fact that these are very well thought out models. And typically when people do this modeling in chemical engineering, that means you take a particular process and then you kind of if you want to put across a very simple methodology to evaluate, like say in this case the pressure drop per unit length, okay, the concept of the fact that this packed bed consists of tubes, and the concept of equivalent diameter, okay, so this is not easy to come up with, right? And the fact that they were able to do it in the 1930s and 40s, and people are using these correlations even to date, okay, in the industry. That's because of the fact that it's a very well thought out model, and um, um, any model that kind of stands for about 10 years is considered to be a really good model. But the fact that this has been there for more than 50-60 years, that means this is one of the really nicely developed methodology for basically getting this delta p by L, okay. And this expression, okay, where delta p by L is equal to V naught bar into mu divided by K, okay, and this K is what is called as a permeability, okay. And if you look at this expression, this K bar has units of meter square, right, because your phi s is non-dimensional, dp square has units of meter square, and other things are all non-dimensional, right. So and this equation is also called as Darcy's law, okay, which essentially states that your the velocity with which a liquid is flowing through a porous media is basically proportional to delta p, which is the pressure drop, and it is inversely proportional to mu, which is the viscosity of the fluid, okay. And if you go back and look up people in other disciplines, especially if you look at civil engineering, you will always come across cases where people are looking at porous rocks, people are looking at flow through sand, for example, okay. So everywhere people kind of use these the flow through packed bed concept to really extract some meaningful parameters. We're also going to look at cases where we're going to say that these expression that we have developed, this Kozeny-Kármán equation, you can also use it for basic characterization of the particles itself, which we're going to look at a little later, okay. That's for the laminar flow conditions. If you want to look at the turbulent flow conditions, so this is the Kozeny-Kármán equation that we developed, as I said, is only for laminar flow conditions. So if you want to develop a similar kind of expression for delta p by L for the turbulent flow conditions, again like we started with Hagen-Poiseuille equation, you'll again have to start with a similar expression, but now for the turbulent flow conditions, right. So it turns out delta p by L for the flow of liquid through conduit in the turbulent flow condition, it goes something like F, that's a friction factor, times rho, that's the density of the fluid, okay, and V naught bar, or say V naught, let me just put it as V naught at this point, okay, V naught square divided by just want to where's that, anyone remembers, that's D, right. Okay, that's your expression for pressure drop per unit length through the pipe, turbulent flow conditions, that's the friction factor, density of the fluid, average velocity with which the fluid is flowing through the packed bed, and D is your diameter of the conduit, right. So again we'll again do exactly the same exercise. You replace your V bar by V naught bar divided by epsilon, that's the velocity with which the liquid is flowing through the packed bed, right, okay, that's the actual velocity, right, that's the average velocity with which the liquid is flowing through the pipe, and then D we are going to replace by D equivalent, right. Can you just do that and let me know what you get for delta p by L for the turbulent flow conditions? Is for turbulent flow conditions, right. Right, so it's going to be delta p by L, you're going to have F there, rho, and your V naught bar is V naught bar square divided by epsilon square at the bottom, and your D equivalent is going to be 2 by 3 into phi s into dp into epsilon divided by 1 minus epsilon, right. Therefore that becomes F into rho into V naught bar square, and this 1 minus epsilon goes up, divided by you have phi s dp into epsilon cube at the bottom, and that's going to be 3 by 2, right? Is that okay? That basically goes something as I am missing a 2 somewhere. Oh, there's a 2 here. Okay, it's actually 2 times f rho v bar square by d. Okay, so there's a 2 here, so therefore this gets cancelled. So you essentially get 3 times f rho v naught bar square 1 minus epsilon divided by phi s dp into epsilon cube. Okay, yeah, so that's and again, you know, we don't know what this f is, right? Again, f depends on your Reynolds number and stuff like that. Okay, again, people have done a lot of experiments, and they have found that, you know, this 3 times f factor, okay, is of the order of 1.75. Okay, again, this is based on several experiments that people have done on packed beds of, you know, different materials. They fill cylinders in the packed bed, they fill ball saddles, you know, spherical balls, okay, and then you make sure that, you know, your Reynolds number conditions are such that, you know, your Reynolds number is greater than 1000, right? So we said for the flow of fluid around particle, we said, you know, anything greater than 1000 up to about 200,000 was the Reynolds number range for which the conditions are turbulent, right? Therefore, so now this 1.75, okay, if it turns out that if you go back and look it up, so say that, you know, I have a Reynolds number condition, okay, of the order of, like, say 10,000. Okay, now what you do is, now I know what is a D equivalent. You use that and you back calculate what is the Reynolds number that corresponds to flow of the fluid through the pipe. Okay, now it turns out that the Reynolds number would be of the order of 4,000. Okay, right? Now from this you can go back to what is called as a Moody's chart, right? MOODY, Moody's chart, right? You can go back and look up, you know, corresponding to a Reynolds number of 4,000, what is your friction factor? Okay, and that friction factor comes up to be something like about 0.01. Okay, all of you know Moody's chart, right? It's basically your Reynolds number, your friction factor versus Reynolds number plot, right? I think you're going to have an assignment where you're supposed to write something about this, if I'm not wrong. Okay, so the point is, now if f, I can go back to f and I can say that your lambda 2, which is the tortuosity factor, now it is actually 3 times 1.75, that's the factor that I've got from experiments, divided by 3 times f. So therefore if you do it, so it's 3 times 0.01, this comes to be 58. Okay, much too larger, right? We calculate this lambda 1 to be 2.1 for the laminar flow conditions. Lambda 2, which is the tortuosity factor for the turbulent flow conditions, is about 58, right? So therefore, so the fact that, you know, this lambda 2 is much larger, that means to say that, you know, it's not that the pipes are more tortuous, okay, it is just that the pipes are as tortuous as the laminar flow conditions. However, because of the fact that there's a turbulent flow condition, okay, what is going to happen is there's going to be a lot of changes in the area. Okay, you know, that means, you know, in some channels the fluid is going to be, you know, flowing in a channel of particular area, and there could be expansion of the liquid at some locations, plus the fact that, you know, liquid is going to turn the direction in which it is flowing. Okay, all that leads to much more larger kinetic energy losses. Okay, and that leads to a larger, you know, you can think about that in terms of the larger value of tortuosity. Yeah, go ahead. Oh, I just said that, you know, so basically, okay, so when we looked up here, right? So, so this is when we did this, right? 3 times f rho v naught bar square 1 minus epsilon divided by phi s dp and epsilon cube. That is for a straight pipe, right? But of course, you know, I would have to have a tortuosity factor lambda 2. So what I mean, these are all based on some of the experiment that people have done. And look, after these you know, development in terms of, you know, correlating your delta p by L to different parameters were developed. Okay, now what people did is they did a series of experiments under different Reynolds number conditions, and then they matched this theory with the experiment, okay, and then that's how these 1.75 and 150 numbers have been obtained. Yeah, so that's what, okay, 3f times lambda 2 is 1.75, and therefore that's why in the next to this thing what we did is I wanted to estimate what is this lambda 2 value, okay, therefore it is 1.7. So if you assume a particular Reynolds number, it will be different, right? Depends on what is the Reynolds number condition that you have in the system. Okay, that means so therefore if I were to take a Reynolds number of the order of like say 1200, okay, of course your lambda 2 that you would have been lower, right? That's because again the Reynolds numbers conditions are such that maybe kinetic energy losses are in that cases are much lesser compared to the case of 10 power 4 Reynolds number. So okay, so that's okay, that's the this expression is what is called as a so I'll go back to the next expression. So this delta P by L, which is 1.75 into rho V naught bar square into 1 minus epsilon divided by epsilon cube into phi s into dp, right? That's the expression that we developed, right, in the previous slide, right? That's your rho V bar square 1 minus epsilon phi s dp epsilon cube and multiply by 1.75. This is what is called a Burke, B-U-R-K-E, Plummer, P-L-U-M-M-E-R equation. Again, these are the two folks which came up with this expression, again in the 1940s. Okay. Now, so we have kind of developed expressions for delta P by L for laminar flow conditions and turbulent flow conditions, and someone called Ergen, E-R-G-E-N or G-U-N, okay, Ergen's equation. So what he did is he said the delta P by L for the entire range, it basically is delta P by L for the laminar flow conditions plus delta P by L for the turbulent flow conditions. Okay. Again the concept is this, right? If you look at Reynolds number, right, this is the inertial force divided by viscous force, right? That's your Reynolds number. Now the pressure drop that you have when the Reynolds number is lower, okay, it is kind of dictated more by the viscous term, and in the case where where you have high Reynolds number, it is kind of dictated by the inertia term, right? So therefore all he did was he clubbed this Kozeny-Kármán equation and Burke-Plummer equation, and he said that if you really are interested in the pressure drop per unit length for the entire regime of flow, all you have to do is sum up these two equations. Okay, so therefore Ergen's equation goes something like this. So 150 into mu V naught bar 1 minus epsilon whole square divided by phi s square into dp square into epsilon cube, okay, plus 1.75 rho V naught bar square, right, 1 minus epsilon divided by phi s dp into epsilon cube. Okay, that's the overall that's the Ergen equation, which basically captures the pressure drop per unit length for the entire flow regime going from all the way from laminar to turbulent. So the point that I want to say is that all this basically assumes if you look at laminar flow conditions, this is the term which basically dominates the pressure drop. Okay, if you go to the turbulent flow condition, this is a term that dominates the pressure loss. However, if you have any Reynolds number in between, there's a contribution of both of these terms to the pressure drop. Okay. Now, if I look at this expression, right? Yeah, go ahead. So I was, I just took some case that was actually given in the book, but the idea is this, right? You assume so if I want to get what is F, right, which is a friction factor. If I want to use a Moody's chart, I should know what is the Reynolds number, right, for the flow through pipe, right? Now what you do is I want to get this Reynolds number. So what you do is if I say that the flow is occurring in turbulent flow conditions in the packed bed, I find out what is the Reynolds number for that condition. Okay, from that I go to this the pipe concept and I back calculate what is the Reynolds number is if the fluid at similar Reynolds number would flow through the pipe. okay, and that turns out to be, in this case about 4,000. And I went to the Moody's chart, and for the Reynolds number, again, it depends on your smoothness and stuff like that, okay. The typical value of f for that case, is about 0.01, okay. That's how it was done. Now, if you look at this Burke-Plummer equation, right, what you can do is I can actually rearrange this a little bit, okay. So, if I say delta P by L, right, I have delta P by L is equal to 1.75 rho V naught bar square into 1 minus epsilon divided by phi s into dP into epsilon cube. What I can do is I can rearrange this a little bit, okay. What I will do is I will have delta P here, okay, and I am going to get this V naught bar, to the other side, okay, and okay, let us say, okay, V naught bar square, right, and then what I am going to do is I have rho here, okay, I am going to get rho also to this side, okay, and that is equal to 1.75 into 1 minus epsilon divided by phi s. I am going to take L to the other side, I am going to write as L by dP, okay, and so I have, okay, what I can do, let me just do this way. I have taken also the epsilon square to the other side, okay. I am going to take V naught bar square divided by epsilon to this side, right. So, therefore, I am going to end up with something like this 1.75 into 1 minus epsilon into phi s into epsilon into L by dP, okay. Now, this is the pressure losses, and this is the, can you identify this, head losses, right, the corrections, right, head losses, right. So, therefore, this basically now that is divided by 2, right. So, now what you do is if I substitute for typical values of what can you say about L by dP? L is the length of the packed bed and dP is the diameter, right, and I can say it what is that? It can tell you something about the number of layers of particle that you have, right. If I have a total bed of height L and dP is your diameter, it will give you, typically it will give you the number of layers of particle that you have, right. Now, if I take some value of epsilon, for example, if I take epsilon to be something like say 0.4, okay, and if I substitute in this, okay, so what I get is a value which is something like I have it written 5.25, okay. This is for L by dP is equal to 1. That means this 5.25 is the, so basically what you are doing is, so in this it basically turns out to be delta P by rho V naught bar square by 2, right, is of the order of 5.25, okay, okay. That is for every layer of, okay, for every layer, because I am taking L by dP as 1, okay, it will basically telling you what for every layer of the particle that I have in the packed bed, what is the pressure losses compared to the head losses, right. And the fact that this pressure drop is 5.2 times this head losses, that means the kinetic energy losses in the case of the turbulent flow conditions are much larger, okay. So, if you were to do a similar kind of analysis for flow through pipes, you will see that this delta P, this ratio will be much less than 1, okay, 1 or less than 1. The fact that this is a much larger number, that basically tells us that the kinetic energy losses in the packed bed, because of the fact that there is a change in the cross sectional area of the conduits through which the liquids are flowing, plus the fact that there is a change in the direction of the fluid, that leads to much higher kinetic energy losses in the case of flow through packed beds, okay. So, that is okay, that is what I wanted to say. Now, it turns out that any questions so far? So, you can also think about doing a, now that we know what is this D equivalent, right, which is 2 by 3 into phi s into dP into epsilon divided by 1 minus epsilon, right. Now, if you take this expression, okay, let us say that I have a packed bed and say that I have filled it up with spherical particles, okay, and say that there is a random packing, and we know that the maximum random packing density, okay, is of the order of 0.64, right. Now if I substitute that value back here, right, and if I say that I'm working with spherical particle, your phi s is 1, okay, so your 2 by 3 into dp times 0.36 divided by 0.64, right, that's your 1 minus, that's a packing density. So it turns out that the number that you get is of the order of 0.375 dp, okay. This is a good kind of exercise to do. What it basically tells you is that that the diameter of the channels through which the liquid is flowing, okay, these are much smaller than the dimensions of the particle itself, okay. In this case is of the order of 0.34, okay, 0.38 or something like that, right. That means the diameter of the channels through which the liquid is flowing through in the packed bed, it is, typically it is always less than the diameter of the particle that make up the column, okay. So that's the it does make sense, right, because of course it has to be less than, because the liquid is basically flowing through the gap that is available between the particles, right. Therefore it is expected that this has to be less than the diameter of the particle, okay. Okay, so maybe I'm just going to end whatever we have discussed on the packed bed, looking at some applications. Okay, of course, I mean, in terms of the applications, we have said, they are kind of used in, all kinds of chemical, unit operations, plus they are used in chemical industries, they are used in, as adsorption columns, they are used in distillation, they are used in, reaction engineering in terms of catalytic bed reactors and things like that, right? But flow through packed bed concept also has been exploited for actually what is called as a particle characterization itself. Okay. So there are a couple of applications that I'm going to talk about. One is a determination of particle size. Okay. Other one is determination of what is called as a specific surface area. Of the particle, right. Again, you have a assignment coming up, right. The next assignment is going to be on particle characterization and stuff like that, okay. So you'll have to write up something about different methods of particle characterization. So this could be one of the method. So basically what you so in doing these particle characterization, what is actually exploited is that if you look at this Ergun equation, right. If you look at Ergun equation, so this is the Kozeny-Kármán equation, and that's the Burke-Plummer, right. And if you look at this expression, your delta P by L, right, it goes linearly with the superficial velocity, okay, and it goes as the square of the velocity in the turbulent case, okay. But if you work with if you work with conditions where your Reynolds number is less than 1, okay, I can actually neglect this, right. Therefore if you were to plot delta P by L, okay, if you were to do an experiment where I measure the pressure drop per unit length across the packed bed as a function of the superficial velocity, what I should get is I should get a straight line passing through the origin, and the slope of this line is going to be 150 times mu 1 minus epsilon square divided by phi s square dp square into epsilon cube, right. So if you work with conditions where your Reynolds number is less than 1, okay, so that this is what should happen, okay. Now if I have way of measuring delta P by L in my experiment, and of course I can also, if I have a way of measuring what is the flow rate, typically what is done is, if you have a packed bed, okay, filled with packing material, what you do is you basically have two pressure tappings, one at the top, one at the bottom. Okay, you connect it to a manometer. Okay, that basically gives you what's the pressure drop, right? You can get this. Okay, I know what is the length of the packed bed. That's your L. Okay, I have a way of getting this. Okay, and once the liquid actually comes out of the packed bed, okay, I can basically collect it, right? I can measure Q, which is the volumetric flow rate. Okay, and volumetric flow rate divided by the cross sectional area will give you what is the superficial velocity, right? So you have a way of measuring this and this. Okay, and then once you estimate the slope, okay, if you have some way of measuring your epsilon, okay, we kind of discussed about a couple of methods, right? And if of course if you are working with the spherical particles, right, your phi s is going to be 1. From the slope I can actually directly get what is the diameter of the particle. Okay, that's one of the applications of Kozeny-Kármán equation, where if you do experiments under laminar flow conditions, I can actually use this delta P by L versus V naught bar plot to get the dimension of the particle. Now again, if you again we'll go with again the same expression, 150 times mu V naught bar, sorry that's wrong, right? That's 1 minus epsilon whole square. Now if you look at this, right, your phi s square into dp, okay, I'll go back to the definition of sphericity, okay, where we said your phi s is 6 by dp divided by sp by vp, right? That's what we said. Therefore your phi s into dp is going to be 6 divided by sp by vp, right, where sp is the surface area of the particle and vp is the volume of the particle, right? Now I can write this as 6 divided by sp into volume. I can write it in terms of the mass and the density. Okay, therefore it becomes multiplied by density of the particle divided by mass of the particle whole square, right? Is that okay? And your sp by m, which is the surface area of the particle per unit mass, that's what we define it as a specific surface area, right? So therefore it goes as 6 divided by say S maybe specific surface area, okay, times rho p whole square, right? Is that okay? No, it's not, there's no whole square, right? Sorry for that. I was talking about this, so okay, there's no, right? Is it okay? So basically I've kind of reworked this. So essentially again it's the same concept, right? So all you're doing is you're, instead of phi s square into dp square, I'm basically expressing that in terms of the density of the particle and the specific surface area. Again I can plug it back into this equation. Okay, so once I do that, if I were to do again a similar experiment, okay, of course I can think about this V naught. So what people do is the moment you do experiments in a column of a particular diameter, right, say this is d, right, what you do is I can basically express this V naught bar also in terms of the volumetric flow rates divided by the area, right? So pi d square by 4. So basically I can basically recast this expression in terms of the volumetric flow rate of the liquid that that is flowing through the packed column. I can recast it in terms of the diameter of the column that makes the packed bed, and also this phi s and dp in terms of your specific surface area and the density of the particle. Okay, if I have a way of measuring, if I know that I'm using a fluid of a particular viscosity, if I have a way of measuring rho p, again we discussed how to get rho p, right, in one of the classes, okay, using what is called the solution densitometry technique. So again a similar plot, okay, delta p by L as a function of either V naught bar, V bar, or or Q if you want to do it. Okay, so again from the slope I can actually back calculate what is the specific surface area, again which is one of the useful quantity, especially if you're looking at applications where catalysis or something where the surface area becomes important. Okay, one of the parameter that for which you would have to characterize the particle is for this specific surface area, and flow through packed bed concept gives you a way of calculating what is the specific surface area. So now commercially people, there are a lot of instruments. There's something called a Blaine's apparatus. Blaine's apparatus, okay, which is a commercially available instrument which is for measuring specific surface area, wherein the concept that we discussed, okay, flow through packed bed under laminar flow condition, that's what is basically used for getting the specific surface area. Okay, you have an experiment in the next semester in which you're going to use this concept for measuring the specific surface area of the particles. Okay. Okay. So yeah, any questions with the? So with that, I'm going to stop with flow through packed beds. Okay. We're going to look at some examples, maybe in the tutorial on Friday, to look at a few problems wherein we're going to look at flow through packed bed. So the next concept that I'm going to look at is something called as a fluidized bed. Okay. Any questions that you have? Yeah. Mm-hmm. No, when you say V naught bar was the superficial velocity. Correct. So all you do is you have a packed bed. This, if Q is a volumetric flow rate, and if it's a circular conduit, you have your cross section area is going to be a circle, right? And Q by A is your superficial velocity, right? Now the fact that the entire cross sectional area is not available for flow, but only part of the area is available. Okay, so therefore what you do is that's V naught by epsilon is how we define, right? So because of the fact that there's a less area available, okay, again it just basically comes from the continuity equation, right? So your Q is equal to some velocity times A, okay, and the same has to again go through this is before it enters the column, the same has to go through the packed column, okay, that is going to be some say if that is V naught here, right, say let's see this is V naught, okay, and now if I say the velocity through the column is V naught bar, okay, that has to be epsilon times A, right, because the volumetric flow rate has to be same across the column. No, what? No. So V naught bar. So epsilon is a void fraction, right? So what is so now this epsilon can go from 0 to 1, right? When you say epsilon is equal to 1, that's when you don't have a packed bed, right? Both the velocities are exactly the same, okay, right? Now the moment I have some porosity, okay, the average velocity is always going to be higher than the velocity with which the liquid is coming just above the packed bed, right? So basically epsilon captures the fact that the velocity goes up when the liquid enters the packed bed. That's the